All right, lesson 211. Today, as we look at the logarithmic function, we're going to be talking about its characteristics, some of its attributes, and we're going to talk about graphing in this form. Now, truthfully, there should be another letter in here, but it gets really confusing. Truthfully, if you remember, this is a vertical, what's it called if you multiply by a letter? Well, we call that a translation, dilation, reflection.
Dilation.
Dilation. Now, if A is negative, then it's not only a dilation, it's also reflection. That's right. Now, the minus C here, what would that do?
That would move the x, like the place of the graph, either left or right.
That's correct. It shifts it left or right, and it'll be an opposite because X is a liar, and we call that transformation a translation. The K would be a vertical translation. Well, there's one in here missing. I did not include the the horizontal dilation, but the rules will still apply. I didn't include it because it was just going to be too many letters. What does this little b right here represent? The base. Now that is not going to be a transformation. The base is just going to be how much the graph naturally grows by or gets multiplied by. That's going to be the multiplier. But so I took off one letter that truthfully should be there, but we'll figure that as we go. I'll show you how that math works, but I feel like if I threw it in now, it just makes all the formulas look really complex, and it doesn't need to be complex. Okay, so we'll see that as we go. First, let's fill in this characteristic chart. I know there's a lot of information here. Let's fill it out. Alexis, make sure with me here. First, given this equation, it says there are some rules where A, B, C, and K are constants with A not equaling. Okay, what do you think A could not equal? Or if it did, it would just eliminate the whole thing. Zero. A cannot be 0. Let's fill that in first. A can't be 0. If A is 0, then it's no longer logarithmic. That gets multiplied out, and all it is some constant function K. Be just a straight line at whatever K is. Now, B needs to be greater than some value. Good guess. It needs to be greater than 0. B, what we'll find out is I did not put this on there. I'm just realizing I needed to. Also, let's do this. Also, B cannot equal 1. B's got to be greater than 0, but it cannot be 1. Alexis. Okay, let's look at this graph here of logarithmic growth. Here, what it's saying is to be logarithmic growth, two things need to happen. First, what makes something growth is if A is greater than 0 and B is greater than 0. Now, if A is greater than 0 and B is greater than 0, we'll have logarithmic growth. Okay, now there's another way you can have logarithmic growth, and it's a little bit different. Now, instead of A being greater than 0, A could be less than 0, meaning negative, but then the base has to be between 0 and 1. Now, why do I say 0 and 1? Remember how B has to be greater than 0? So B always has to be greater than 0. I need to check this. That was there. B needs to be greater than 1 there. Sorry. A is positive and B is greater than 1. Here, if A is negative and your base is between 0 and 1, then it would still appear to be growth. What's up, Gabby? Now, let's jump over to decay. Now, decay is going to be a different situation here. So instead of A being greater than 0, A is less than 0. Now, this is when B is still greater than 1. So if B is greater than 1, but A is now negative, it'll be decay. Or if A is now greater than 0, meaning positive, but the base is between 0 and 1, now we have decay. On either of these situations, the domain range will be the same. How far to the left does this graph appear to go?
0.
To the y-axis, x equals 0. What about over here? 0. Now, because of transformations, you could say usually it's going to be 0 to infinity, meaning going left to 0 but right forever. However, because of this transformation, we could be shifted. So I'm going to, instead of saying 0, I'm going to put the letter C. So if you want to, you might want to say usually 0 to infinity, but because of translations, we could be shifted C units. Remember, C is a liar. That's why over here is C positive or negative.
Negative.
Over here, C is negative, and so C is a liar. So X's are liars, so I'm gonna put it as positive. So I'm gonna put C to infinity. By the way, you don't have to change infinity, whether you add C or subtract C. infinity is still represented by infinity. Okay, what about the range? How low does this seem to go? Negative infinity, how high? Positive infinity. This is going to be negative infinity to positive infinity, all reals. Unless we have some restriction, it's going to be all real. So the domain is usually going to be 0 to infinity, but because of transformations, it could be C units. Okay, so there's those slides. Let's scroll on down. Let's talk about increasing versus decreasing. Logarithmic functions are always, well, let's see, what's this one always doing?
Increasing.
It's always increasing. What's this one doing?
Decreasing.
Decreasing. So they're either always increasing or always decreasing. You know what they never do?
They stay the same.
They never change direction. They never change directions. So what do you think this blank is? Never. They never change direction. So they have no relative local extrema. What did extrema mean? That was a big word that we learned in Unit 1.
The maximum.
Maximums or minimums. That have a maximum, if you look at my hands here, it's like a top of a hill. To have a maximum, you have to change direction. Think about it. To have a maximum, you'd have to change direction. That would create a maximum. Or if you wanted a minimum, you'd have to change direction from decreasing to increasing. Since we don't have any change direction, there's never any extrema. Unless on the closed interval. Remember, if we cut off and said, hey, we're only looking from, say, 1 to 8, then we could say this value is a max, this value is a minimum. Okay, that's what that note means right there. Let's talk about concavity. What's it mean to be concave up or concave down? We'll look over here. What was this one here? Down. This one's concave down. What's this one mean? If you remember, that meant that A rock, the average rate of change, is either always increasing or decreasing. Logarithmic functions. Let's talk about this one, the A rock. If you were to measure the slopes all the way around the like instantaneous slope, meaning the immediate slope right at these spots, what's the slope doing here if you were to draw like lines?
Increasing.
Ooh, you would think so because the function's increasing, but like this slope would be really steep, not so steep, less steep, less steep. You see what's happening to my slopes as we go along here? They're decreasing. You see how they're always decreasing? That would make this graph concave down. Logarithmic functions are always concave up or always concave down. This one would be concave up. This A rock, even though the function is decreasing itself, the A rock is constantly increasing. So the slope is getting more and more, I should say less and less negative. It's increasing. This slope is getting less and less negative as you proceed on. They never change concavity. Since we don't change concavity, they have no points of inflection. Point of inflection is when you change from concave up to concave down or vice versa. All right, let's finish this up. So the limits. This is saying what's happening to the y's as x approaches c from the right side of the graph. Another way of saying this is a limit doesn't tell you where the graph is. A limit tells you where the graph is going. Now remember, c represents the shift here. C would be like this end. Now, as we get closer and closer to the value of C, whatever C is, in this case, it looks like the y-axis. As we get closer and closer to the y-axis, what's happening to my y values? They're decreasing. Put negative infinity there. Now, this is saying not where the graph is, but where it's going. As the graph approaches positive infinity on the x-axis, meaning as we go right, as the graph travels to the right, what's happening to the y values? They're increasing. They're increasing. So if it's growth, that would be your limits on a log. If it's growth, they would look like that. So what's going to be different if it's decay? Well, what happens as we approach this C value, the asymptote? They're going to increase. The graph's going to rise. And then what's going to happen as we go to the right? Decrease. It's going to fall. Whoops, I didn't do that right. Negative infinity. There we go. So there's a whole bunch of properties for a log. And we have more. Couldn't fill it on all on one slide. There were so many of them. Okay, so now let's talk about some of this nitty-gritty math that I was telling you about earlier. So I already gave you this slide here, but this time I filled that in, so we don't have to fill it in a second time. What I want you to look at is the asymptote that it'll approach is based off of this transformation here. Now, I want to point this out to you. I don't want to complex it. Let's just say there was another letter thrown in here. I'm going to use the letter D because I haven't used that. What if there was a number? I'll just put a number here, like 3. Now that 3, what does it look like it's doing to x? Multiplying. Does that mean I'd actually multiply? No, what would you do instead? Divide. So when that comes up today, instead of just saying the asymptote is at C or whatever the opposite of this is, you would end up dividing it by 3. Just to remind you of that. That's how horizontal dilation will work. But I didn't want too many letters, so I didn't put that in there. But that happens there. And then here's some key points. And again, the same thing. If there is a number in there, the x value would get divided by whatever that number is, or you do the opposite of what it says to do. So anyways, there's all these points. Rather than explaining what all these mean, I'm going to use examples just to show you. Okay, so slide on down. It says here, graph the following equation. I'm going to start with the asymptote that's just above here. To find the asymptote, you look to the inside. With a logarithm, the value over here, this is rule 3 over on my chart. If you look in the domain rules, rule 3 tells you that you cannot take a logarithm of a non-positive number, meaning what's on the inside has to be greater than or equal to 0. So the domain here would have to be x is greater than or equal to what number? I'm skipping the math. Let me show you. Greater than 0, not equal to. I said that wrong because it has to be a, you cannot take a logarithm of non-positive, which means it has to be positive. It can't be equal to 0. Okay, how would I solve that? -2. So this is what I was saying on the previous slide. If x has to be greater than -2, this would go in the parentheses as the domain from -2 to infinity. So what's happening at -2 is you have a vertical asymptote. So go to -2 on your graph and add in a vertical asymptote right there. So the graph will approach that vertical asymptote, but it'll never actually get there. That's x equals -2. That's where that is. So that's the first key point from this box right here. There's 3, if you want to graph a logarithm, there's basically 3 things you need to do. First, place the asymptote. Second, we're going to place the x-intercept. Almost always your asymptote will be 1 plus or minus the inside transformation, comma 0. Now, if you have a k at the end, which is not that normal with logarithms, then you would shift it and it would no longer be an x-intercept. But typically, like this one, we don't have a vertical asymptote. So the point starts here unless you have a transformation. It'll be at 1 comma 0. That's the base point. Now, do I have a transformation here? Yes. Which way is that telling me to go?
Left.
Left 2 units. So this x-intercept will actually be 1, 2 units right there. So what this math says right there is you take your 1 and you add it to C. Now, C is this number here, but it's a liar. So here's the math. For the x-intercept, here's how the math would look. You would take 1, and instead of adding 2, what do we do instead of adding by 2? You subtract 2. And so what do you get there? -1 comma 0. And that's exactly where I placed it. See that? Okay, finally, the next key point is at a y value of 1. Now, the way to kind of think through this, I know this looks really, really tricky. And I'll show you what this means later when we have a base between there. But the way to think about this is add your base and your C point together, then add A and K together. So what is this saying? Add the 2 values that seem to be on the inside and the 2 values that seem to be on the outside. So I know this is going to seem complex at first, but it'll start to make sense in a second. To find your next key point, what we're going to do, I'll just do KP. What does KP stand for? Okay, y'all don't know. I'll write it out then. Key point. To find a key point, what I'm going to do is I'm going to add my B plus my C. So in this problem, what's the B? B stands for base. What's my base? 3. And you add your C value. C value comes from the inside. Now, is it actually +2?
No, it's -2.
Okay, so it'll be 3 minus 2. And then the y value is a plus k. So a is the number in front of the log. How many logs do I have? 1. K is the number after the log. 0. So when I simplify this, I'll get my other point. What is 3 minus 2?
1.
And here?
1.
1. Okay, so the point is there. Now from this point, how you can get the others is you're going to be multiplying by 3. Do I multiply x's or do I multiply by y's?
1.
Do you remember? For a logarithm, you actually multiply your x's. They're going to be getting multiplied by 3 as you go. I didn't place that point in the right spot, did I? Where's 1, 1?
Oh.
Right there. So you're actually going to start multiplying your x's. That's how you do that. Okay. So
Would be what, 2, 3?
so if you multiply this, if you multiply 1 by 3, what do we get?
3.
So if we go 1, 2. No, wait, I need to get to 3. Sorry. That's 1, that's 2, that's 3. And that would be adding up 1. I'm going to check that one. I don't know if that's not seeming right to me. We'll check it. Let's plug it in here. We're thinking at x of improve my math here, 3. Let's do this real quick before we make a big mistake. Let's go to your calculator. Check our table here. So I'm going to go to graph. Where was that log button? By the way, on Delta Math, at this point in time, once you have your asymptote 2 points, you can just click the little graph button and then put the graph on. By the way, you have everything you need for your homework. But for us to make sure our packet looks right, you do Control 10 to the power of x, and that's where you find that. Log 3, x plus 2. So that's the graph I'm looking for. So log base 3 of x plus 2, press enter. And I want you to hit Control T to get a table. Now, what were the points we've already had? We had 1, 1, right? What was the other point we had? Was it negative 1, 0? So we got those 2 points. And where is the next point that they're seeing? 7, 2. That's the next point. 7, 2. That's what I was saying. It wasn't looking right to me. 1, 2, 3, 4, 5, 6, 7, 2. Okay, so I'll explain to you now why it's at 7, 2. If you're wondering why is it there, because the multiplier needs to be. You remember how we had this transformation? Remember how the x-intercept was at 1, then we subtracted 2. The key point was at 3, then we subtracted 2. That's the multiplier. That's just getting multiplied. So what's 1 times 3? 3. Does that make sense? To find the next point, you would multiply this 3 by 3. What's 3 times 3? 9. And so the next point would be like that. You would say this 3 times 3 is 9, so it'd be 9 minus 2. And then you'd come over here and you just continue to add by 1. Since this was at 1, now I'd say 1 plus 1, and you'd get the 2. If you wanted one more point, what's 9 times 3? It'd be 27 minus 2. And since this becomes 2, it's now 1 plus 2. So you'd have 25 comma 3. Let's go over to your table. And let's see if we have 25 comma 3. Do we have that point? Yeah, that's how it works. So that's what how the transformation works. For you, though, you only have to know 2 points. That's why I only put those 2. All right, let's jump over to the next. On the next, by the way, will we call this logarithmic growth or decay? Growth. Okay, good. Let's go over to the next one. I'm going to start with the asymptote. At the asymptote, all you have to look at is the inside. With a log, they cannot be anything but positive, meaning it cannot be a non-positive number. So the way you would solve for your domain or your asymptote is you would say that x minus 1 has to be greater than 0. So how would I solve from there? You would add 1. And so x has to be, whoops, not d, x has to be greater than 1. So that's going to be where we place our asymptote. We're going to place our asymptote at x equals 1. So at x equals 1, that's right there, place your asymptote. That's where our asymptote goes. We have to be on the right side of this graph. Now we're going to use the x-intercept. So this one is actually, see how I have a k value of 2? Won't actually be an x-intercept. I'm going to use this formula right there. So it won't actually be an x-intercept. So I could say x-intercept plus 2. When I call it an x-intercept plus 2, what I mean by that is it's not actually going to be an x-intercept. It's going to be 2 units up because of this transformation right there. So how would I do that? I take this formula, 1 plus c comma k. So my 1, and then what's my c value? If it says -1, do I actually subtract 1?
No.
What do I do instead? And then my k value is, whoops, why did I put plus 2? I'm sorry. It's 1 plus 1, comma. And then over here, my x-intercept is no longer just 0. I add this and I do the truth because it's on the outside. So it's going to be up 2 units. So what's 1 plus 1? 2. So we go right 2, up 2. That's our, what would have been our x-intercept point. Now my base, is my base greater than 1 or is it between 0 and 1?
Between 0 and 1.
So the easiest way to use this is right here, which means I'm going to take the reciprocal of the base. So what is my base right now? 0.5, which is the same thing as what fraction? So what this is telling you is take the reciprocal of, that's 1 over b means the reciprocal. So this key point, I'm just going to do KP this time. What does KP stand for? Key point. I'm going to take the reciprocal, which now is 2 over 1. Right here. It's going to be 2 over 1. And then my c. Do I actually subtract 1?
No,
You add 1. Good. And then I take the opposite of a. So what's the opposite of a? Plus 1. And I add k. What's 1 plus 2? 3. Let me write the math in. 1 plus 2. Because my a was a -1. You do the opposite of a. Okay, so when I reduce this, what's 2 plus 1? 3, and 1 plus 2? 3. We'll plot that point. So this graph should look like this. Now, if you're on Delta Math, all you have to do is after you place the asymptote and those 2 points, you can press the connect to graph and it'll do that for you. Now, what would happen here is all these original x values will get multiplied by 2. You see how it goes from 1 to 2 there? The next one, you would take the next point, if you wanted to get this graph right, is you'd multiply this 2 by 2. What's 2 times 2? 4. So the next point would be 4 plus 1. And then over here, you remember how you just keep adding 1? It was a 2, then it was 1 plus 2. This would be 1 plus 3 because 1 plus 2 is 3. So now it'd be 1 plus 3. So our next point would be at 5, 4, if you want to get that accurate. 2, 3, 4, 5, 1, 2, 3, 4. I should have had it go right through there if I wanted to have it graph perfectly. And we could check this out if you wanted to. Do you want to check it or move on? Check it. Let's check it. So I'm going to hit Control T to make the table disappear. Tab up to get my equation. All right, we had a negative in front of the logarithm. I remember that. It was a negative log, and our base was 0.5. Now here I want to check with y'all. Was it x minus 1? X minus 1, and then a plus 2 on the outside. Okay, so that's the equation we're checking out. Press Enter. Control T. Was the first point we had 2, 2? Do we have 3, 3 as our next point?
Yeah.
And then 5, 4?
Yeah.
Were those 3 points we found? Great. Looks right. All right. Here's some DOLs for you to try. Just find those 3 pieces of information, the asymptote and the first 2 points, and then connect your dots. Okay. Okay, picking up. So as I said, your asymptote is based off of that a logarithm, the domain must be a positive number. So the asymptote starts whenever this would be at 0. So what you do is on your domain here, the domain would be that x minus 1 has to be greater than 0. So what would you actually get? X equals 1. No, I'm sorry, not x is equals 1. X is greater than 1. That's would be where you place your asymptote, though, is at 1 itself. So you won't, an asymptote means where the graph approaches, but it does not just equal it. It approaches that. A vertical asymptote, anyways, it'll never actually hit. So we'll never get to the value 1, but we'll approach the value 1. Now from here, the x-intercept without a transformation, I'm just going to say it this way. Let me try it different. Rather than using the table, maybe this might be easier to think of it this way. Without a transformation, the x-intercept is at 1, 0. And your key point without a transformation, would be at the base, 1. Now, without a transformation, that's where these would be. Do I have transformations on this problem? Yes. What is this telling me to do here? Go right 1. This is with no transformation. I need to write that in there. No transformation. With no transformation, you have this x-intercept. And again, this would also be no transformation. Now, we do have transformations. This says go right 1. So which number do I change? The x. So instead of being 1, I need to go 1 plus 1. And do I have a vertical transformation? Now, is this a liar or truth teller? Truth teller. So I need to add 2. What's 0 plus 2? 2. So you should have the point at 2, 2. That would be 1 point that you would need. And the last point you would need is where? Let's come over here. To this point, what is my base? My base is 4. Now, do I have any transformations? Yeah, it's the same transformations as here. What happens to the x value, the base? I need to add 1, so it'll be 4 plus 1. And then what about my y? Do I leave it alone as a 1? No, what do I do to it? I add 2. So what is 4 plus 1? 5. 1, 2, 3, 4, 5. And 1 plus 2 is 3. Now that's what you'll need for delta math. You'll click graph, and then it'll come through. Whoops. It'll come through and connect it for you. Goodness gracious. And it'll look like that. Is that growth or decay?
Growth.
Growth. And so this would be the same way. It's probably easier for you to do it like that. To think through starting with these 2 basic points and then performing transformations. Just do the transformations. Remember, outside is a liar or truth teller? Truth teller. So the y's will get multiplied by 2. And the inside, liar or truth teller? Liar. So what will happen to the x values? Subtract by 3. So as you go through these 2 points, just do the transformations on the 2 points, and it'll probably be easier for you to get the values like that. Okay, moving on. That last one's a DOL anyways. Example 2. We want to write limit statements. So now we're going to practice limits for the end behavior of the following log functions. All right, this doesn't have an arrow right there. I'm going to add it to your graph. On this one, to the best of our abilities, what does it look like as we go left? What x value does it appear that this graph is approaching? It doesn't actually get there, but where's it going?
0.
0. I agree. So you'd say LIM f of x equals underneath x arrow. X is approaching 0. Now, is it approaching? Does it actually get to 0?
No.
No, it's approaching there, and it's approaching from the right side. You need to have that little plus. That means we're coming from the right side of 0. We don't come from the left side of 0. We're coming from the right side of 0. Now, what's that going to be equal to, or what's happening to my y values? As we get closer and closer to 0 from the right side, what's happening to my y's? They're decreasing, they're falling. What symbol represents falling forever? Okay, that would be the first limit right there. Now, what about this limit? Okay, what is happening to my x's? They're increasing without bound. That means they're going to infinity. It's going right forever. What's happening to my y's as we go right forever? They're also increasing. Okay, do you remember what this would look like as a graph? Okay, well, I'll tell you, what would happen is your x's get multiplied by 1/3. So if I had a point, I'm trying to think through my head starting at like 27, because 1/3 would work well for 27. Like if you had x values and y values, and you start, I know it's going to seem backwards as I go through this. If I start at 27, you would then multiply by 1/3. What's 27 times 1/3? 9. What's 9 times 1/3? Okay, and what's 3 times 1/3? 1. Okay, so usually if you go back, we said that we had the key point at 1,0. You tracking? I just got to this 1 value for x. It's normally 1, 0. This has a vertical transformation. You need to multiply it by 2. So what's 0 times 2?
0.
So it's still 0. Now, as we go backwards, as I go this way, what's happening, because these are decreasing, these would be decreasing by 1 as well, except for they're multiplied by 2. So instead of actually subtracting by 1 each time, we're actually going to be subtracting by 2, I believe. So this would be, what number minus 2 is 0? 2. So as I go backwards, it would look like adding. This would be 4. This would be 6. Okay, what would that look like as a graph? Let's find out. 0, 1, 0, 1. No, I have this backwards. Sorry, 1, 0 would be right there. 3, 2. No, I'm doing this wrong. It doesn't look like that. I'm doing it backwards. Well, this is supposed to be decay. I was trying to walk you through why it's decay, but I messed up these numbers. This is decay. I'll prove it to you in case you're like going, how is that? Let's just look at it over here. I should have done it this way to begin with. It was 2 log 1/3 here. Just an x, correct? Okay, hit Control T. Okay, we had 0, 1. Do we have that point? 3, we did positive. Yeah, that's where I messed up. Okay. That's a -2. That's going to be -4. That's going to be -6. There we go. Let me see if that's right now. What was our other point? We had 9. Do we have 9 -4 now? And 27. -6, yeah. Okay. Oh, I know why I was backwards on it, because I didn't reorder these. That's why. Yeah, because they're supposed to be, yeah, okay. Anyway, sorry. There it is. So it's decay. So if it's decay, the graph looks like this. Here's our logarithmic graph. You want to just do a quick sketch. Your graph should look like that. So let's talk about the limits. What would this limit be? What x value does it look like it's approaching?
0.
0. That's because there's no shift there. So x is approaching 0, and is it doing it on the right side of 0 or the left side of 0? Put a plus there. This one's called g of x, so limit of g of x equals, what's happening to the graph as you approach 0 from the right side? It's increasing to infinity. And what's happening to our limit as we go to the right? Again, this is g of x. What's happening as x increases with that bound? What happens as we go to the right here? Decreases, it falls. And so those would be your limits. Brings us to our next round of DOLs. All right, you go ahead and write the limit statement for these two. Oh, this is interesting. This just says log without a base there. It's a 10. Very good. That would be a 10. That would be a 10. Oh, wait, go ahead. All right, now moving into example 3. So now we're going to start looking at the same functions. So keep track of those functions. I'm not going to be giving you just new ones over and over. We're going to keep diving into the same type of functions. We want to determine if this function is increasing and decreasing, which means from there we can figure out concave up, concave down. First, what's this function doing? Increasing or decreasing? F is increasing. What in the world? Let's try that again. F is increasing. Now, does that mean it's concave up? No, really what concavity has to do with is the delta AROC. How is the AROC changing? So as we go, what's happening to my immediate slopes, if you will? Is the slope increasing? If you went and started drawing a bunch of slopes, like little slopes, like barely touched it. I'm drawing what's actually called tangent lines. If you drew a bunch of tangent lines, what's happening to the slope of each subsequent tangent line? It's decreasing. So would I call this concave up or concave down? It's concave down because F is concave down since delta AROC is less than 0, meaning the AROCs themselves are decreasing. They're getting smaller and smaller. The change is a negative. It's going down. Each one is getting less and less. Each tangent line. I threw this down just as a review from unit 1. It'd be concave down. Okay, what about this? We already graphed this. What did this look like before? Was it growth or decay? Do you remember? This one was decay. So looking at the decay graph, okay, this time is G increasing or decreasing? G is decreasing. Is it concave up or concave down? Meaning, is my AROCs increasing or are they decreasing?
Increasing.
That's right. Yeah. So G is concave up since delta AROC is greater than 0, meaning, just translation, the AROCs average rate of changes are increasing. That's all that means. Whoops. Okay. The AROCs are increasing. If delta AROC is greater than 0, that means the AROCs themselves are increasing. And over here, if delta AROCs are negative, that means the AROCs themselves, the average rate of changes themselves, are decreasing. That's all that means. So that was a review from Unit 1. I don't want you to forget Unit 1 stuff. All right, your turn. You're going to look at the same two functions that you just previously had on your last DOL. Same two functions. So if you've already graphed part B, know what it looks like, you can use that to help you. Determine if H itself is increasing or decreasing, and if it's concave up or concave down. Do that for both A and B. All right, example 4, selected values of several log functions are shown in the tables below. For each table, find the value of the constant k. Okay, so if we're dealing with logs, what does that mean is going to be happening to my x column? Multiplied. What's happening to my y column? Being added. Okay, so let's check it. 1, 2, 3, 4, 5. Does that look good? Okay, so over here it needs to be multiplied. 1 becomes a 2, 2 becomes a k, k becomes an 8, 8 becomes a 16. What is k gotta have to equal?
4.
4. Why does it keep going to red lines? Okay, the k has got to equal 4. This is a multiplier by 2. That was a multiplier by 2. This was an adding of 1 all the way down. That was the rule, if you will. Okay, what about over here? What's the rule? Let's check out the one that's not missing anything. What's happening to my y column? They're adding by 5. Okay. What's happening over here? 6, 18, 54, 162. Multiplying by 3. So if I went backwards, what's the opposite of multiplying?
Right.
What's 6 divided by 3? 2. Good. Yep. Okay, let's look at part C. Oh, this one's interesting. Let's again start with the simple. What's happening to my h's? They're adding 7. Okay, let's see what's happening over here. E to the negative 2. Do you remember what that means?
E's the natural, right? 2.71.
It is roughly 2.71, but you remember what it means to have a negative power?
Oh, it's the fraction.
You could do the reciprocal. This is like 1 over E times E. I'm gonna write it this way. And then what happens here? That's just E. We don't know what K is, but we know this one is E times E times E times E. That's 4, 5, 6, and 7. Okay, so what appears to be happening?
Adding E's.
How many E's am I multiplying by each time? I went from negative 2 to 1. That means this got multiplied by 3. Let's check that. If I multiplied this E by this E that's right there by 3 more,
E4.
and that would give this E7 and this E10. Would that make sense? That's E to the 4th. Very good. So each time we're multiplying by E cubed. That's the rule here. This is multiplying by E cubed. Multiplying by 3 E's. Yeah, once it gets fast. Okay, your turn. I'll let you try this one. Okay, so a hint on this one is that there has been some type of transformation. I want you to take away the transformation, to think of it this way. If you take away the transformation, meaning if you did x plus or minus some number, so I'll say x plus c. If you took away a certain amount, all of a sudden it'll start to make sense to you. For example, how much is this adding by?
1.
How much is this increasing by? 2. So it goes from 1 to 2. Remember, it's got to be a multiplier in a second. And then this one, we just skip 1 and we now increase. So I want you to think, if you added or subtracted a number here and made your new list, all of a sudden it'll start to work out. Give you a hint. Subtract by 3 and see what the table starts to look like. You subtract by 3. All right, so now let's take a look at example 5. So if we're talking about find any asymptotes, with the logarithm, it has one asymptote. It'll have a vertical asymptote. And remember, it occurs where the inside logarithm becomes equal to 0. So on this problem, do I have any horizontal transformations inside here? Do I have any horizontal transformations? No. So the asymptote, remember, the domain comes from saying x has to be greater than 0. So there's no transformations. The asymptote itself will be where it equals 0. So in this case, it would be x equals 0. This would be a vertical asymptote. A vertical asymptote. Logarithms have vertical asymptotes, not horizontal, but vertical asymptotes. That would be the asymptote there. Okay, on this one, if I was looking for a domain, I would say that x minus 3 has to be greater than 0. Well, the asymptote begins right where this domain is approaching. So how would I solve algebra here to get x isolated? We would add 3 to both sides, and so x has to be greater than 3. What does that mean my vertical asymptote will be located at? X equals 3. Very good. Okay, now some of the questions I've had in the years past are about students that are saying, wait, why we're saying vertical asymptotes and we're not doing vertical transformations. So here's how it makes me think of. Show me right now with your arm a vertical line. Okay, now take your vertical line and I want you to double it. Multiply it by 2. Maybe we have a vertical dilation. What happens to your vertical line if you double that line?
Here's longer.
Okay, but what's the definition of a line?
Never ending.
It never ends. So it's already a vertical line that never ends, and now you double it. So now what does it do? Does it never end twice?
Yes.
Does that even make sense? To never end twice? It doesn't change at all. Okay, I'll do another one. Take your vertical line and now shift your vertical line up. What's happened to your vertical line?
Nothing.
Nothing, because it already goes forever both ways. So that's why a vertical asymptote is not affected by vertical transformations, because it's already a vertical line that goes from negative infinity all the way up to positive infinity. It doesn't matter how you change it, it's still a vertical line that goes up forever. So you don't have to worry about anything. You only do the inside transformations. Okay, so here is the one I talked about earlier. Remember how I said sometimes you might have a number here? But I don't want to throw off the math. Let's just work through what happens. The domain, what has to be true of a logarithm?
You cannot take the logarithm.
I'm a non-positive. So x plus 1, 3x plus 1, excuse me, has to be greater than 0. 3x plus 1 has to be positive. So we go to solve this. What would we do first?
Subtract 1.
Subtract 1. Good algebra. So we have 3x is greater than negative 1. Now what? We divide by 3. And at this stage, try to get a different color there, sorry. We now find out that x has to be greater than negative 1/3. Very good. Now, if that's what it has to be greater than, that means we have a vertical asymptote. And where is that vertical asymptote located? Forgot the word asymptote, sorry. Vertical asymptote would be located at x equals negative 1/3. That would be the vertical line that the graph approaches, but it never actually gets there because it's greater than it. But it would approach that line right there. Again, that's a vertical line that stretches up and down forever. So even though you multiply it by 4 out front, has no effect. Multiplying a vertical line by 4 is still a vertical line that goes up and down, positive and negative infinity. So it makes no change on it. All right, with that, I'll let you try your DOL. Find any asymptotes in this logarithm. All right, to finish up, we're going to find the domain and range of the following log functions. Okay, for this one, would this be growth or decay? If your a is greater than 0, meaning it's positive, it's a positive logarithm, and your base is greater than 1. That would be growth. The y being multiplied by 2 would just make it grow faster, but it is growth nevertheless. It's just a growth that's growing twice as fast as normal when it has a 2 out there. So that's logarithmic growth. What would this domain be if there is no transformation on the inside? X has to be greater than 0, or you could state it this way. What's the smallest this graph, or the smallest x value this graph approaches? 0. Does it ever get there? No, that's why it's a parenthesis, where we go towards it, but we never actually get there. How far right does the graph go? Now, does it ever get to infinity? No. That's why it's a parenthesis. So you can write it either way. That would be our domain. You could write it either way. Okay, what about this? Oh, we have to do range as well.
Negative.
All right, what about the y's? How low?
Negative.
Negative infinity, how high?
Positive.
So using interval notation, you would say y is all reals. And interval notation, oh, that means with inequalities. No, this is interval. I'm sorry. With inequalities, you don't write infinity, so you just say it's all reals. Okay, and with interval, you'd say negative infinity, comma, positive infinity. Okay, all right, let's jump to G. This time the log itself is negative. The base is 2. So is 2 a growing number or decaying number by itself? Growing, but we have a vertical dilation, which means it's now going to be reflected. So is this growth or decay? Decay. And we get shifted which way? Right 3. So 1, 2, 3. I want to put my asymptote there. You know, I should have included my asymptote on this one. Okay, and now I want to put my asymptote here. This is decay this time. And it'll decay really fast because of being multiplied by 5, negative 5. So let's talk domain here. X has to be greater than what number?
0.
Not 0, greater than
3.
3. Okay, which in using interval notation, it's 3 to infinity. Okay, what about my range?
All real.
Again, all reals and negative infinity to positive infinity. That should be the range of every logarithm unless it's restricted. Okay, one more. The base of 1/2. If you're multiplying x's by 1/2, are they growing or decaying? This would be decay. Now you multiply it by 4. Is it still decay? Yes, still decay. Even though you're multiplying by 4, that's multiplying the y values. I'll put it that way. Not multiplying. So the it's still decay. So we have a decay going on here. Let's see, which way would it be shifted?
Minus plus 1 to
To the left.
Left 1 at first. First left 1, and then how do you get rid of that 3? Divide it by 3. So it actually would not be at, I'm gonna try to put it at 1 first. You would first say, okay, left 1, and then you divide that by 3, and it goes to negative 1/3. That's where we should be. X equals negative 1/3. Let me go ahead and put this x equals 3, even though it's easy to see. That's negative 1/3 there. We're saying this is decay this time. Because the x's are getting multiplied by 1/2. So that's decay. Now let's talk through our domain. How far left does this graph travel?
close to negative 1/3.
Yeah, so here's the algebra. 3x plus 1 has to be greater than 0. What would you do first? Subtract 1. And so 3x has to be greater than negative 1. Now what would you do? Divide by 3. That's where we got the negative 1/3 from. And so there's the domain. X is greater than negative 1/3. Or you could do it negative 1/3 to infinity. And our range? All reals. Negative infinity to positive infinity. Okay, I want to wrap with one thing. I know you have a DOL, but before we do the domain here, I want to wrap with one thing. To try to put together the whole lesson. The key attributes that I want you to know, there's 3 key attributes. 3 key attributes. This is a takeaway, if you will, your takeaways. Take away from the lesson. 3 takeaways I want you to know. There's 3 key attributes. The first is a logarithm. Can a logarithm itself be negative?
No.
Can a logarithm be 0? No. So first is the asymptote. The asymptote at x equals whatever would make x equals 0 inside the log. If that makes sense. Asymptote occurs where x would equal 0 inside the logarithm. Okay, that's the first key takeaway. The second key takeaway I want you to know is the x-intercept. let's do the standard. I'll do this. The standard x-intercept is 1, 0. So why do I say standard? Is start from there and then apply your transformations. That's the easier way. I should have done the lesson that way. At the very start, I realized it was confusing putting the formulas down. Just the standard x-intercept is 1, 0, but then apply your transformations from that. Meaning, if you're supposed to, if you have an x minus 2, you add 2 to that value. If you're multiplying by 3 on the outside, multiply your 0 by 3, so on. Okay, and then the other key point. You remember that other key point? Standard key point was base, 1. So again, on this, start there and then apply your transformations. That will be a whole lot easier for finding your point if you do it that way. So if you have the graph or anything like that, I would do it in that order. Okay. So I'll leave you now with your DOL to do, and I'll come around and check your packets.